Hey, hello everyone. Can you hear me?
Yes.
Okay, good. Feels like I'm not heard. Okay, so welcome back to our final session. We will have 2 or 3 talks. The final speaker haven't confirmed yet, so we don't know whether we will have the final talk. But now Timothee Corsini will present his talk about temporal, simple temporal graphs, or even.
Well, a bit larger than that, but thank you.
Okay, please, over to you.
So, hi everyone. Today I will tell you about temporal graphs, like the purpose of this workshop. And my study here will be about reachability in temporal graphs, and more importantly, depending on which setting we allow, whether we allow straight journeys, simple graph, proper graph, we'll see all of this. This is a joint work that we did with my PhD supervisor, Arno Castex, and an intern that we had last summer, Ritika Sarkar. So to start, what is a temporal graph? Well, you should know. We can see that as a sequence of finite graph. And here we consider a finite sequence. We call this finite graph snapshots. And usually we just represent them with a graph with edge labeled with time, such that the edge is present at such time. And if it's not the current time, the edge is not there. If we forget about the labels and we take only the graph with every edge that appears at least once, we call it this graph the footprint of our temporal graph. In a temporal graph, there's a notion of things that changes, and we need to define a new notion of path. And you should know that too. Journeys, or temporal path, are simply path that uses the edges in chronological order. To give an example, with the graph given here, we can see that there is a path from B to E crossing A, then C with time 1, then 2, then 4. But we can see that this is not symmetric because E cannot reach B because it reached C at time 4 and then it's stuck here. And if we allow non-strict journeys, we could go to A afterwards, but we are still stuck and we cannot reach B. So journeys make things more complicated, but that's what makes it fun. And with this, we can define the notion of reachability, which is basically a vertex can reach another if there is a journey from this vertex to the other. And if every vertex can reach every other vertex, we say that the graph is temporally connected. So now that we define that, we need to check some important things about temporal graph. The first thing that is important to verify, and that is not always told explicitly in the literature, is the notion of strictness of journeys. The fact that we allow a journey to use edges at the same time or not. In the previous example, we can see that if we were allowing non-strict journeys, we could have a journey from E to A, but that's not the case if we are only in strict journeys. So that's important to say that at the beginning. And actually, there is some families of temporal graph where this notion of strict or non-strict vanishes. It's proper temporal graphs. In that case, properness is the same idea as properness of colors, being that 2 edges cannot share the same sets of time labels. So in that case, if you are in a proper temporal graph, you will say that every snapshot is a matching, and you will not have non-strict journeys. Every journeys will be strict. And there's also other simple way to see the temporal graphs. One of them is a simple temporal graph, being that an edge is equivalent to a temporal edge, being that an edge appears only once and not more than that. And if we combine proper and can we still hear me because I'm not sure about that? Let me just quickly close. Okay, if we combine proper and simple, we get what we call a happy graph. Yeah, can you? Okay, maybe it's better. Thank you. If we combine, so what I said is, if we combine simple and proper, we get happy because it's the simplest model. and that we defined here. And hopefully, some results could be simpler in terms of complexity. So we'll see that actually, so all these definitions have some importance, and we'll see that in an example of a problem being the spanner problem. So the spanner problem in temporal graph is the same idea as the finding a spanning tree, but this time with a temporal graph. You have a temporally connected graph, and you want to reduce its size such that it's still temporally connected. And whether you consider to minimize it in terms of edges or in terms of total number of labels used, well, the answer will be different, and will also depend on whether you allow strict or non-strict journeys. So we can have, given graph G1, 3 candidates as optimal spanners. G2 would be a spanner, it's a subgraph of G1, if you can see, a spanner in the non-strict setting that use the least number of edges and also the least number of labels. While if we are forbidding non-strict journeys, then G3 would be an optimal spanner in terms of number of labels used, because there's only 4 labels used. And G4 will be an optimal spanner in terms of edges used, because we have 3 edges used. So it matters. And actually, the problem of spanner is, as we saw in previous talk, it's not always close to a tree, because we can have, in some specific way, if we, for instance, if we allow strict journeys, we could have very dense spanner. For instance, you take a click and you put the same label on everyone, and you're in the strict setting, then the graph is temporally connected. But if you remove anything else, it's not temporally connected anymore. So now I will give a quick overview of all the setting we defined before, and see that there's some inclusion. So if so we can see that actually we have a strict world and a non-strict world that are clearly distinct from each other. But then if we are in proper, this notion of strict or non-strict vanishes. So if we are in a proper graph, we do not care on which setting whether we are strict or non-strict. And we have the fact that some type of graph will be simple, but in the strict model, some other will be simple in non-strict model. And finally, if we are both simple and proper, we are happy. And in that case, we don't care about strict or non-strict again. And the blue arrows here means that this is simply inclusion of a setting. If you solve a problem inside of this one, well, it doesn't mean anything outside, but if it's very hard inside one, it will be hard outside. And if it's easy in one of in strict, for instance, it will be easy in the inside classes. And now we'll see how we'll actually distinguish these classes in terms of what we call reachability, and we'll define what exactly we mean by that. So how do we capture the expressivity of a configuration? It's, like I said, through reachability. You define the reachability graph, which is simply you have your graph, and you have a directed graph based on your temporal graph that has the same set of vertices, but has an arc from one vertex to another, if and only if there is a journey from this vertex to the other. It's the same notion of the transitive closure in static graphs. So in this example, we can take the temporal graph G, and we can define 2 types of reachability graph. The first one is if we allow strict journeys. In that case, you can see that everyone can reach everyone except E that cannot reach D, B, and A. And if we allow non-strict journeys, the reachability graph will be the same, but this time E can reach A. And with that, well, we know that we want basically to say that we want to see if every type of reachability graph in terms of directed graph can be obtained from a temporal one. And the answer will depend whether in which configuration we consider. And we'll first see that some configuration are distinct based on the reachability graph that can be obtained. So the first separation is the easiest, trivial. It's very trivial. It's to separate strict and simple from non-strict, meaning that there is a graph in the strict a reachability graph that exists in the strict and simple model, and that cannot be obtained from any non-strict graph. And this graph is basically to a path of length 2. Okay, so it's obtained from this graph in the strict and simple model. And if we wanted to obtain it from the non-strict model, well, we would need to use the same vertices. But then if we need to add an edge between A and B, which has some time label T and maybe some other time labels. And then we also need to add an edge between B and C. Otherwise, we have no journeys from B to C. And this one will have time T prime and some other things. And no matter the relation between T and T prime, since we are in the non-strict setting, this will imply an arc between A and C in one way or another. So this reachability graph cannot be obtained in the non-strict setting. And we'll see that this is a kind of separation, but there's some other ones that separates our classes. So these classes are distinct in terms of reachability obtained. The strict model cannot be obtained, not all strict graph can have their reachability in the strict and simple model. Not all non-strict graph and simple one can be obtained in happy, and not all proper ones can be obtained in the non-strict and simple model. So that defines some separation of settings. And we'll see that some settings can be translated into others while keeping exactly the same reachability graph. So we'll see that. The first one is between non-strict and strict. I can turn any non-strict graph into a strict one while keeping the same reachability graph. And we call this method the saturation method. And it's quite simple. You consider every snapshot and you take their transitive closure, this time in terms of static graph. So basically, if you have a connected component, you turn it into a clique. And you do that for every snapshot. Okay? And so what that means is that if there was a journey in the non-strict model between two vertices, then in the transformation, it will be there will be an edge between these two vertices. So if you have a journey that uses the same sequence of edges with the same time label, you can just change it by using one single edge with one given time label, and you have a strict journey. So you have an equivalence between the existence of journeys, and you do not create new journeys in terms of, you do not, if two vertices could not reach each other, you still have this property. But the graph is quite different because we added edges and obviously time labels. But that's still interesting. We'll see that actually there's another transformation that is a bit stronger, which can turn every non-strict graph into a proper one. It's called the dilation method. And this one will keep the same footprint, but will add a lot more time labels. To do that, you still work with every snapshot locally. And you will say, okay, if I have a snapshot that has a long path inside, I will simply duplicate the snapshots so that I have enough time to take the edges one by one. So you take G1, the first snapshot, and you duplicate 2 times because you have a path of length 2. And for G2, well, you do it 3 times because you have a path of length 3. Okay. So in that, and you do the same for G3 and G4. So in that situation, you know that you get a graph with the same edges, and you are still you know that there is a path in the journey in the non-strict model, and this one is turned into a strict one, but you have not yet a proper graph. So how to turn this thing into a proper one? Well, consider the first 2 snapshots created by our transformation. These ones will have, so if you combine them, the first one will be at time 1, the second one will be at time 1 plus epsilon. And to turn it into a proper one, you simply need to add a constant to each of these labels that is distinct between adjacent edges. So you add, for instance, C2 to the time labels of the first edge and C1 to the time label of the second edge. And this constant will be strictly less negligible compared to epsilon, distinct from the other constants, and also negligible compared to 1. In that case, you will see that you get always distinct time labels. And in that case, your graph is proper. And to find these values, well, basically you obtain them from a proper edge coloring of your footprint, of your input graph. So that's it. And this operation is, you can compute it easily because you can find not an optimal number of colors, but you can take delta plus 1 and in a polynomial time. So delta being the degree of the maximum degree of a vertex. And so with that, there's one last step if you want integers. You simply turn every epsilon and constant, and you simply take them in order, increasing order. And if you add this graph as an input, you get this graph at the end, which doesn't look, in terms of edge of time label, it seems hard to read, but the point is that you still use the same edges and you do not create new journeys in terms of edges used. So that's the end of this transformation. And now we'll just see an overview of our settings. We see that in terms of expressivity of reachability graph obtained, the happy setting, which is both proper and simple, is the least expressive one. It is strictly included into the simple and non-strict setting, which is itself strictly included into the proper and non-strict setting. And these two are equivalent because proper is included into non-strict, it's a special case, and we can turn every non-strict one into a proper one while keeping the same reachability. And finally, these two are strictly included into the strict setting. And there is one last setting, which is the strict and simple setting, and which is strictly more expressive than happy and strictly less expressive than strict. But even if we know that it cannot be turned into the non-strict ones, we do not know if the converse is also the same. We do not know if there are some transformation from the non-strict settings to the simple and strict one, or if there are some counterexamples. So that leaves two open questions. Anyway, in this model, we see that the set of reachability graph is very small. I mean, not very small, but it's the smallest one in the happy setting and the highest one in the strict setting. So the happy setting is the least expressive in our models, and the strict one is the most expressive. But there's one last transformation that can turn every strict one into a happy one. While not keeping exactly the same reachability graph, it will keep the same induced reachability graph. But I will not cover it today because I think that's the end of my presentation. So thank you for your attention.
Any questions? Maybe from online participants? From offline participants? Please.
Go a couple of slides before.
Yes.
Stop.
Okay.
Yeah, here. You said that it's essentially open if simple and non-strict is a subset of simple and strict.
Yes.
And whether non-strict is a subset of simple and strict.
Mm-hmm.
So is it if let's say the left open problem is proved to be included, does it imply anything for the right problem or vice versa?
Well,
Are these completely independent?
no, they're not completely dependent. If you manage to say that, for instance, this one cannot be translated into this one, this implies that these two cannot be translated.
Can you say
either.
which one is which? Because the people online cannot
Sorry.
see the pointer.
If you say that simple and non-strict cannot be turned into simple and strict, it will imply that non-strict cannot be turned into simple and strict because of the inclusions. And on the other way around, if you can prove that non-strict or proper, because these are equivalent, could be turned into simple and strict, this would imply that simple and non-strict could be turned into simple and strict.
So proving the left one is easier.
I wouldn't say that it's easier.
It's easier because the right one implies the left one.
Well, yes, but maybe it's not easier. It doesn't mean that it's easier to prove it.
Okay, it's weak. It's a weaker statement. It's a weaker statement.
It's a weaker statement. Yes.
Good. Thanks.
Any other questions? Yeah, I have one small, maybe stupid question. Can you go a bit
back
forward?
Oh,
yeah.
Okay.
To this picture, yeah. So happy means that all edges get only one label.
Yes.
And every vertex has edges, incident edges have different pairwise different labels, right?
Exactly.
So if we consider a different model where all labels are pairwise different and every edge gets only one label, is it the same as happier or it's strictly happier?
It's the same.
The same? Okay. Okay.
You will basically you can turn every, because in terms of reachability, you could say, oh, if you put a label on every edge, you could just distinguish them, because if you have two labels, if you have two edges that share the same label, you could just say, oh, okay, one is I will put it at a higher value that is distinct from the other, because they cannot communicate between each other. There is still a way to transform it that way.
Okay, is it easier to use this setting where you have every vertex gets different pairwise different labels?
Well, it's interesting if you have if you want to have some equivalence. So if you want to enumerate, for instance, all happy graphs, you could find it better if you find some equivalence between the labelings, and that way it's easier to have it's better to have some labelings where two edges share the same label but are not.
Okay.
That was the.
It's also valuable in order to be able to use lifetime as a parameter. So I was working on a problem where I was looking at only unique time steps everywhere. But of course, then you can't use lifetime as a meaningful parameter. Whereas with happy graphs, the only thing you need is that you have enough time steps to edge color the entire graph.
Yeah.
Okay. Thank you, Dave. More questions? Okay, if not, then let's thank the speaker again.
Thank you.